Okay, Walker, so we're at 2. Pert and Nert, properties of exponential graphs. Warm up. June is opening her first savings account and is depositing $100. The bank offers 3% annual interest to be calculated at the end of each year. 1. Write a function A of t to model the amount of money in Juno's savings account after t years. That equation is A of t equals 100 times 1 plus 0.03 to the t. 2. Calculate the amount of money in Juno's savings account at the end of 1 year. Okay, so let's go ahead and do that. So then that's 100 parentheses 1 plus 0.03 to the 1, which is 103. Dollars. Okay, let's take a look at 3. Calculate the amount of money in Juno's savings account at the end of 5 years. Okay, so that's 100 parentheses 1 plus 0.03 to the 5, which is $115.93. All right, go and finish up those problems. You have calculated interest compounded annually using the exponential equation in the form of A equals P parentheses 1 plus R to the T. How does this equation change when interest is compounded as more frequent intervals? Can interest be compounded continuously? Let's take a look at the next page. Number 1. Cut out the exponential graphs and equations located on pages 779 and 781. Match each equation to its graph. Sort them into a growth or decay function and attach them onto the graphic organizer located on this page. Then complete the table. Okay, let's take a look at the first graphs. First graph is exponential equation, and the equation is f of x equals 2/3 to the x. Okay, so let's substitute -1 in for x, so that's 2/3 to the -1. That's 2/3 to the 0 equals, and then 2/3 to the 1. Okay, let's go ahead and plug that into our calculator. So 2 divided by 3 raised to the -1 is 1.5. Two divided by 3 raised to the 0 is 1. And then 2 divided by 3 to the positive 1 is 0.7. All right, go ahead and finish that up. Let's take a look at the second graph. Second graph is exponential growth, and the equation is f of x equals 1.5 to the x. So that's 1.5 to the -1, 1.5 to the 0, and 1.5 to the 1. Let's go ahead and plug those into the calculator. 1.5 to the -1, 1.5 to the 0, 1.5 to the 1. All right, go ahead and complete that table. Let's take a look at the third graph. The third graph is exponential growth, and the equation is f of x equals 3 to the x. So that would be 3 to the -1, 3 to the 0, and 3 to the 1. All right, let's go ahead and plug that into our calculator. 3 to the -1, 3 to the 0, 3 to the 1. All right, go ahead and complete that table. Let's take a look at the next graphs. All right, first graph is exponential decay, and the equation is f of x equals 1/3 x. So then that's 1 divided by 3 to the -1, 1 divided by 3 to the 0, and 1 divided by 3 to the 1. Let's go ahead and put that into our calculator. All right, go ahead and fill in the table. All right. So next graph is exponential decay, and the equation is f of x equals 0.1 to the x. So that would be 0.1 to the negative 1, 0.1 to the 0, and 0.1 to the 1. Let's go ahead and plug that into our calculator. So 0.1 to the negative 1, 0.1 to the 0, and 0.1 to the 1. All right, go ahead and fill in that table. All right, last graph is exponential growth, and the equation is f of x equals 10 to the x. So that'd be 10 to the negative 1, 10 to the 0, and 10 to the 1. All right, let's go ahead and plug that into our calculator. All right, go ahead and fill in the table. And let's take a look at the next page. Activity 2.1, key characteristics of exponential functions. Go ahead and mark off this question. Question 2. Which b values for the function f of x equals b to the x produce neither growth nor decay? Provide examples to support your answer. Any b value that are equal to or less than 0 or equal to 1 produce functions that are neither growth nor decay functions. Let's take a look at the next page. 3. Write an exponential function that satisfies the given characteristics. A. Increasing over negative infinity to positive infinity and a reference point of 1, 6. Okay. And to verify the reference point, if we do f of 1 equals 6 to the 1 equals 6. Okay. And we know that all exponential functions are increasing from negative infinity to positive infinity or decreasing from negative infinity to positive infinity. So B, decreasing over negative infinity to positive infinity, the reference point is negative 1, 4. So to verify the reference point, that's f of negative 1 equals 1/4 to the negative 1, which equals 4. All right, go and finish up 3A and B. All right, number 4. Summarize the characteristics for the basic exponential growth and exponential decay function. All right, go ahead and read over it and complete the table. All right, let's take a look at the next page. Activity 2.2, the natural base C. Helen is opening her first savings account and depositing $500. Suppose she decides on a bank that offers 6% annual interest to be calculated at the end of each year. That equation is A of t equals 500 parentheses 1 plus 0.06 to the t. 1. Write a function A of t to model the amount of money in Helen's savings account after t years and determine the amount in the account at the end of 1 year and 5 years. Okay, so let's go ahead and do that. So then that's 500 parentheses 1 plus 0.06 to the first power and 500 1 plus 0.06 to the fifth power. All right, so it's $530 and $669.11. All right, let's take a look at number 2. Suppose that a bank decides to start compounding interest at the end of every 6 months. If they still want to offer 6% per year, how much interest would they offer per 6-month period? If they offer 6% per year and are compounding it twice a year, that would mean that the bank offers 3% interest per 6 months period. All right, let's take a look at number 3. Go ahead and mark out number 3. All right, let's take a look at number 4. Write a function to model the amount of money in Helen's savings account at the end of T years, compounded K times during the year. So A of T equals 500 parentheses 1 plus 0.06 divided by K raised to the K times T. 5. Determine the amount of money in Helen's account at the end of 3 years if it's compounded twice a year, monthly, and daily. All right, so let's go ahead and calculate that. So that's 500 parentheses 1 plus 0.06 divided by 2 raised to the 2 times 3, and 500 parentheses 1 plus 0.06 divided by 12 raised to the 12 times 3. Oh. Now, it just occurred to me, and you have to be careful, that the times 3 didn't go in the exponential, so I need to fix the first one by putting in parentheses 2 times 3, and then you see it's in the exponential. So 500 parentheses 1 plus 0.06 divided by 12 raised to the parentheses 12 times 3. So 500 parentheses 1 plus 0.06 divided by 365 raised to the parentheses 365 times 3. All right, so that's $597.03 for twice a year, $598.34 for monthly, and $598.60 for daily. All right, number 6. What effect does the frequency of compounding have on the amount of money in her savings account? The more often the account is compounded, the faster her amount of money increases. All right, let's take a look at the next page. Recall that in question 4, the variable K represents the number of compounded periods per year. Let's examine what happens as the interest is compounded more frequently. 7. Imagine that Helen finds a different bank that offers her 100% interest. Complete the table to calculate how much Helen would accrue in 1 year for each period of compounding if she starts with $1. All right, go ahead and read over and complete that table. Let me zoom in there because those numbers get kind of small. All right. 8. Make an observation about the frequency of compounding and the amount that Helen earns. What amount is it approaching? As the number of compounding periods increases, the amount of increases, it's approaching the value of 2.72. Let's take a look at the next page. The amount that Helen earns is actually an irrational number called E. E equals 2.7188281828459045 ... It is often referred to as a natural base E. The symbol E is used to represent that constant 2.718281. It is often used in models of population changes as well as radioactive decay of substances, and it is vital in physics and calculus. The symbol for the natural base E was first used by Swiss mathematician Leonard Euler in 1727 as part of a research manuscript he wrote at the age of 21. In fact, he used it so much, E became known as Euler's number. The constant E represents a continuous growth and has many other mathematical properties that make it unique, which you will study further in calculus. Question 7. You showed that the expression parentheses 1 plus 1 divided by k to the k power approaches E as k approaches infinity. You can use this fact to derive the formula for the compound interest of the continuous compounding. All right, go ahead and read over the worked example. All right, let's take a look at the next page. Number 9. Suppose Helen's investment of $500 in her savings account is compounded continuous at a rate of 6%. How much would be in her account at the end of 1 year and 5 years? At the end of 1 year, the balance in her account would be, let's go ahead and put that in our calculator. So that would be $530.92 after 1 year. At the end of 5 years, the balance in our account would be, let's go ahead and plug that into our calculator. So that would be $674.93 after 5 years. 10. The given functions are sketched on a coordinate plane. Shown. Label each function. C. Using the functions f of x equals 2 to the x, g of x equals 3 to the x, and m of x equals e to the x, approximate the value of f of 2, g of 2, and m of 2. All right, so let's go ahead and do that. So that'd be 2 squared, 3 squared, and then e squared. All right. Let's take a look at the next page. Activity 2.3. Modeling population change with E. In the previous activity, you explored the continuous growth of a principal amount using the value E. How can E be used to model the population changes? 1. The formula for population growth is N of T equals N naught E to the RT. Describe the contextual meaning of each quantity. All right, go ahead and read over and complete the table. All right, 2. Why is E used as the base? The constant E is used as the base because the population is continuously growing. The population doesn't increase at set intervals, such as every minute or once a week. It changes continuously. 3. How could this formula be used to represent a decline in population? I could change the rate of growth to a negative value to represent a decline in population. Let's take a look at the next page. 4. The population of the city of Fredericksburg, Virginia was approximately 19,360 in 2000 and has been continuously growing at a rate of 2.9% each year. A. Use the formula for population growth to write a function to model this growth. That function is n of t equals 19,360 e to the 0.029 t. B. Use your function model to predict the population of Fredericksburg in 2020. So we're going to use the equation n of 2020 minus 2000 equals 19,360 e to the 0.029 times 2020 minus 2000. Okay, so let's go ahead and do that. All right. So the population of Fredericksburg in 2020 would be 34,578. C. What value does the function model give for the population of Fredericksburg in the year 1980? So we can use the equation n of 1980 minus 2000 equals 19,360 e to the 0.029 times 1980 minus 2000. All right, so let's go ahead and do that. So the population of Fredericksburg in the year 1980 would be 10,840. 5. Use technology to estimate the number of years it would take Fredericksburg to grow to 40,000 people, assuming that the population trend continues. Okay, so we're going to graph y equals 19,360 e to the 0.029x and y equals 40,000. Let's go ahead and do that. All right, and y equals 40,000. Now we don't see anything, so we need to adjust the. Now let's go ahead and do 0 to 100 and 0 to 50,000. All right. So there you go. You can now see your graph. You see your point of intersection, and that's what we want. So the population of Fredericksburg would grow to 40,000 after the year 2025. All right, let's go and take a look at the next. All right, the student works 1 and 2. Let's take a look at the next page. The student works 2A, 2B, 2C, 2D, and 2E. Mark out this question. All right. Stretch. It has been called the most beautiful equation in all mathematics. The equation links together four of the most important constants in math, including E and the imaginary number e to the in plus 1 equals. Three of these constants are shown. The right-hand side of the equation is the fourth constant. What is it? What does the expression e to the in tell us? To research this equation, the fourth constant on the right side of the equation is e plus 1 equals 0. It means that the expression e is equal to negative 1. The student works 1a, 1b, 1c, 2a, 2b, 2c, 3a, 3b, and 3c. All right. Go and start working on your assignment and have a wonderful Wildcat day.